Hello guys, so today we will be presenting our project, which is the engine blower for air intake. So we will do the engine blower for our project. So what is engine blower? Engine blower are a mechanism used to supply continuous airflow to the engine to enhance the engine performance or cooling. So it is commonly used in internal combustion engine, HVAC system, and also industrial machine. So in this project, we will examine its working principle and focusing on the interplay between the shaft-driven impellers and aerodynamic forces to generate airflow. So this model will illustrate a simplified blower system, which including the intake, impeller housing, and drive component. So the objective of this project is firstly to design a functional engine blower model. This design will help us to understand the working principle of centrifugal air induction, and also we will visualize the component interaction between the impeller, shaft, and housing. And also we will analyze the airflow direction and housing efficiency.
For description of mechanism, the first one is blower housing. So it contains the impeller and it directs air from the intake to the outlet using centrifugal force. The second one is air inlet. So it is a rectangular duct for ambient air intake. It designed to minimize turbulence. So the third one is impeller or shaft assembly. It is a conical shaft, connects motor to impeller. It spins to generate centrifugal airflow. The fourth one is motor or compressor unit. It is a fine cylinder, acts as motor or air compressor. It provides power to rotate the shaft and impeller. The last one is, of course, the mounting base. It supports all the components.
Hello, I'm Muaz. I'll be presenting CAD for the design. So, this slide presents the full CAD assembly of my engine blower project, modeled using AutoCAD. The design integrates three major systems: the piston cylinder mechanism, the impeller, and the outer housing. The goal was to simulate how linear motion from the piston produced by internal combustion can be transferred to the impeller to generate airflow, similar to how a mechanical blower works in real engines. The model focuses on achieving proper alignment between the moving parts and maintaining compactness for practical use. Creating this CAD assembly helps us visualize mechanical interactions, motion transfer, and overall layout before fabrication. So the next slide. In this slide, I've highlighted the key component of the design with more detail. The piston and cylinder assembly is the core of the design where pressure build-up simulates combustions to push the piston. This motion is critical in driving the next stage, which is the impeller and the blower unit. It is positioned after the piston is designed with curved blades to convert the linear motions into rotational airflow, acting as the main blower. Also, the last part is the housing structure serves as the framework. It holds all the parts in place, maintains alignment, and directs airflow through an inlet and outlet channel. These breakdowns allow us to analyze how each part contributes to the system and also help us in identifying areas of optimization like friction reduction or improving airflow path.
Next, in this part, we focus on analyzing how velocity, force, and torque behave in the system. We calculated the velocity of different parts to understand how fast they move during the operation. Next, we look at force and torque, especially the torque applied at the crankshaft, which is important to ensure efficient power transfer. These calculations help us better understand how the blower performs in real-world conditions.
Here are the simulations that we conduct by using linkage software.
So moving on, here now we have the graph analysis of our results. The first graph shows velocity versus crank angle, where this helps us see how the speed of motion changes throughout the rotation. The second graph is torque versus crank angle. It tells us how much turning force is produced at different points. And then the third graph, net force versus crank angle. This graph shows that the total force acting on the components during a full rotation. Well, these graphs are useful to visualize how performance varies and to spot any points of high stress or inefficiency. Next, we're going to delve into the discussion of this project. Well, this engine blower is a fully mechanical system that doesn't need electricity. It uses a motor to spin an impeller which pushes air outward using centrifugal force. It's great for things like engine cooling or supporting combustion, while the design is simple, reliable, and easy to maintain. With features like cooling fans, a stable base, and a direct shaft connection, we modeled and tested it using AutoCAD and Autodesk Inventor. While airflow depends on motor speed and proper alignment is key, where overall it's a cost-effective and practical solution for steady airflow. Last but not least is the conclusion. So to conclude, this engine blower successfully shows how mechanical system can create steady airflow without needing electricity. It uses a centrifugal impeller driven by a direct shaft, making it efficient and reliable. The design is simple, compact, and affordable, with a focus on durability and stable operation. We also address common issues like bearing wear by improving shaft alignment and overall structure. In the end, this makes the blower a strong, long-lasting solution for cooling, ventilation, and industrial use. That's all from us. Thank you.